Hello everyone, thanks for tuning in. We're going to talk about nuclear chemistry today, and we're going to start off with a little bit of a review. And remember when we talked about atoms way back when at the start of the course, we had two things that we used to identify the atoms, the atomic number, which is Z, and the atomic number, if you remember right, is the number of protons inside of the nucleus. And then we've got the mass number, which is A, and notice there the first and the last letters of the alphabet, and it is the number of protons and the number of neutrons added together. And if you recall, right, so the atomic number determines what type of element you have. So if it's 1 proton in the nucleus, right, it's hydrogen. If it's 92 protons in the nucleus, it is uranium. But the mass number, right, can vary for a given element because the number of neutrons can vary. And you'll remember that we call them isotopes when they've got the same atomic number, but they have different mass numbers. And earlier on, we basically just kind of ignored the fact there were isotopes. We said that the average mass is used in all our calculations, but we really didn't talk too much about the difference between one isotope and the other. And so this is where we're going to kind of pick up again. So for instance, if we look at carbon, carbon exists in a couple of different forms. We've got carbon-12 and we've got carbon-13. And the number up top is the mass number, so that is A. And the number down below is the atomic number, so that is Z. So in this carbon atom here, we've got 6 protons. And in order to have a mass number of 12, we must have 6 neutrons because 6 and 6 make 12. And if we look at the atom down below, we can see that this has 6 protons as well. Otherwise, it wouldn't be carbon. But it must have 7 neutrons in order for 6 and 7 to add up to 13. And so remember that these are isotopes of the carbon element. What's really cool is that some isotopes are actually unstable. So the carbon-12 and the carbon-13 we just looked at, they pretty much live forever, or at least for billions of years. But there is an isotope of carbon called carbon-14, and carbon-14 actually does not live for too terribly long. Every 6,000 years or so, half of the atoms actually break down and they form nitrogen-14. And they also give off an electron. And we're going to write this as follows. This is what we call a nuclear reaction. So instead of a chemical equation with a chemical reaction, this is a nuclear equation describing a nuclear reaction. And this should really give you the heebie-jeebies, right? Because up to now we've said you balance by making sure that you've got the same number of atoms of each element on the left as the right. But clearly here we had a carbon on the left, and here on the right we've got a nitrogen. And where did the carbon go? And the answer is it is no longer in existence because carbon has changed into nitrogen. It's also given off an electron. So this is the formation of a brand new element here, right? So this is what makes nuclear chemistry so exciting, is that we get to form brand new elements. And this electron here, actually, it shoots out of the nucleus. So the nucleus actually changes and makes the carbon turn into nitrogen. And you get a ray of electrons shooting out of the element. In fact, this is why we call it radiation. So the particles that are given off from the nucleus emanate out in a ray or in a straight line. So what's going on here, right? So what's going on here is if you peer inside of the nucleus, so carbon has 6 protons and 8 neutrons, okay, and during this nuclear reaction, one of the neutrons actually breaks down, and so instead of getting 8 neutrons, you've got 7 neutrons, and that neutron actually turns into a proton, so instead of having 6 now, you've got 7, and in order to keep the charge balanced, right, you have to form an electron, and so that electron comes off as a ray, right, so hence radiation. So the stream of particles coming out of the nucleus, right, is the radiation that it's produced. So in essence, right, what you have is a neutron turning into a proton plus an electron. And we'll describe this later on, but what's kind of interesting is that the rates of these nuclear reactions are completely unaffected by temperature and pressure and a catalyst, right? So we said earlier that the rates are normally affected by temperature, pressure, and catalyst, but for regular reactions that may be true, but for nuclear reactions that is untrue. As far as we know, we can't speed it up or slow it down at all. And the other exciting thing is the amount of energy you give off. You are looking at sort of 100 million times more energy. So that is an enormous amount of energy. And just to kind of put that in perspective, right, imagine your car is powered by a tank of gasoline, and that gasoline can probably get you about, let's say, 400 miles or so, well, it's actually burnt in a chemical reaction. Now, imagine your tank of gasoline was made out of radioactive gasoline, and we use the energy from its breakdown. Well, instead of getting you out about 300 or 400 miles or so, it would get you 300 or 400 miles times by 100 million, which is an incredibly large number. I mean, essentially, you would just give your car to your grandkids and their grandkids and their grandkids, and you get 100 million times the range on a single tank as you would as if it were just gasoline in a chemical reaction. So that really makes you think, huh?